Okay. Ready. Let's gather review. It's working. Okay. All right, how do I get rid of this? There we do it. Can you hear me? Can you
Yeah.
hear me? Good. Mhm. How is everyone today?
Pretty good.
Yeah.
Good.
Hi, Elliot. How have you been?
Well, California's still burning down.
Well, I'm sorry to hear that. Is it red where you are, Dave, in the sky?
Well, it's actually was really apocalyptic red a few days ago, and that stopped when the layer stopped being up in the sky and came down to meet us, and now it smells like fire. Yeah, I know, right? You can't win.
Yeah. All right. Is it time to start?
Yeah.
All right. So I hope this will be review for most of you. If it's not, let me know. And following Dave's suggestion, I'm going to try to do landscape instead of a portrait. See if how that goes. All right. So let me start with a few basic definitions. Oh dear. What's wrong with my pen?
You're in eraser mode. You either tap it twice or tap the pencil.
Thank you. There we go. So basic definitions. We're interested in functions from a smooth manifold to the real numbers, C infinity functions. We say that P in the manifold is a critical point. If the differential of F at P vanishes. Otherwise, it's a regular point. A real number is said to be a critical value if its pre-image has a critical point, and otherwise it's said to be regular. The T is a regular value. Okay. And notice that if T is regular, then its pre-image in the manifold is a smooth codimension 1 submanifold by transversality. All right. The next object is a, if you will, a second order invariant at a critical point called the Hessian. So P is going to be critical here. So P is a critical point for F. And we'll get to P in just a second. Given the map F, we can form the differential of F, which we can think of as a map from the manifold to the cotangent bundle of the manifold. Its value at a point P is simply the differential of F at P, thought of as a linear map from the tangent bundle of the manifold of P to R, which is an element of the dual bundle to the tangent bundle. So that's an element in the cotangent bundle at P. Well, I shouldn't say P here, I should say X. This is true at any point. Okay, so P being a critical point is equivalent to dF at P lies in the 0 section of the cotangent bundle. Okay. Now, if we look at the tangent bundle to the cotangent bundle at a point along the zero section, let's say P0, that canonically splits as the tangent bundle at P of M plus the cotangent bundle P at M. This is a general fact about vector bundles. Along the zero section, well, you always at every point have the vertical tangents to the fiber of the bundle. But along the zero section, you also have a complementary space, a horizontal space, namely the subspace tangent to the zero section at that point. So that gives you a decomposition of the vector bundle along the zero section as the sum of the tangent bundle to the vector bundle, as the sum of the tangent bundle to the manifold, and a copy of the vector bundle at that point. In this case, our bundle is the cotangent bundle, so we get this decomposition. This is, in this case, the tangent bundle to P at M, and this is the cotangent bundle to P at M. That's P, and you have this direct sum decomposition. All right, so given that direct sum decomposition, we can then form we can think of the differential of F at, well, the differential of the differential of F at the point P0, so P is a critical point, so, well, sorry, at the point P, sorry, at the point P, will then be a map from the tangent bundle to M at P, well, into the tangent bundle, the cotangent bundle at P0, but I've now decomposed that as the tangent bundle of P plus the tangent bundle, the cotangent bundle at P. Of course, the first component of this map is just the identity. The second component, pi 2, composed with D of dF at P, is in a map from the tangent bundle of M to the cotangent bundle of M at this point P. And that's called the Hessian. Now, if you give local coordinates in a neighborhood of P, you can make the same definition at any point. Those local coordinates give you a trivialization of the tangent bundle in this neighborhood, and that trivialization provides you a splitting, just like we talked about along the zero section, a splitting at every point, but away from the zero section, that splitting and therefore the projection to the second factor depend on your choice of local coordinates, or more generally, you get a splitting by taking a connection on the bundle, will depend on the connection. But at along the zero section, so at a critical point, this decomposition is canonical. It requires no choices. It's independent of any coordinates you use. And that's what gives you the Hessian at this point. Okay. Now we can compute the Hessian in any local coordinates. So we compute it in local coordinates. So first of all, df of x is simply in the trivialization. The local coordinates provide both the trivialization of the tangent bundle by the partial derivatives and a trivialization of the cotangent bundle by the differentials of the coordinate functions. And so df at x will be given by x and partial of f with respect to xi dxi summed over I. That's the formula for df in these local coordinates. And then the differential of df of x, well, it's the identity in the first factor, and it turns out to be the matrix given by second partial of f with respect to xi with respect to xj dxi tensor dxj if you sort it out. Okay. So the Hessian, I've now written it as a bilinear map from the tangent bundle tensor itself to the reals rather than a map from the tangent bundle to the dual of the tangent bundle, is given by the matrix of second partial derivatives at the point. And the basic fact, of course, is this is a symmetric matrix. So that says the Hessian is self-adjoint. If you think of the Hessian, as we are doing, as a map from the Hessian at P is either a map from the tangent bundle at P to the cotangent bundle at P, then its dual, the dual map, is equal to the Hessian, which means that with respect to a basis and a dual basis, the matrix is symmetric. Now, any symmetric quadratic form, any quadratic form or symmetric form on a finite dimensional real vector space can be diagonalized. So there exists a basis for Tm, maybe not the one coming from the original coordinate system, but there is a basis so that H of P of F is given by a diagonal matrix. And in fact, you can multiply the diagonal entries by any square by changing the basis, and the diagonal entries will take the diagonal entries to be plus or minus 1. So there is a basis in which this form is diagonal with eigenvalues plus 1 and minus 1. You change the basis here and take the dual basis there. In other words, in terms of matrices, the Hessian is some matrix H, and you're multiplying by A transpose A to turn this into a diagonal matrix. And then you can make a diagonal with plus and minus ones down the diagonal. The index of the Hessian, the index of any quadratic form, is the number of strictly negative eigenvalues when you do this decomposition. So the number of minus ones in this decomposition. I guess I should have said plus minus 1 and 0. The Hessian may be degenerate. All right. So that's our Hessian. It's a symmetric form on the tangent space at a critical point. And we say that F is non-degenerate. Sorry. We say that P is a non-degenerate critical point for F. P is a non-degenerate critical point for F if the Hessian at P of F is non-degenerate, has only plus and minus 1 eigenvalues. Degenerate. Okay. So only plus and minus 1 eigenvalues. And as we will see, a Morse function is a function all of whose critical points are non-degenerate. But before we talk about Morse functions, let me give you a local model for what a function looks like in a neighborhood of any non-degenerate critical points. This is a purely local lemma, so we might as well work in Rn. So let U, Rn be a neighborhood of the origin. and f, a C infinity function with 0 as a non-degenerate critical point. Okay? Then there exists an open ball in Rn, neighborhood of the origin if you want, and a diffeomorphism phi of V into U, sending the origin to the origin, so that F compose phi is the value of F at the critical point plus summation epsilon I xi squared. I equals 1 to n, epsilon I is plus minus 1. So not only is the Hessian, let's suppose for just a moment for simplicity that F vanishes at the origin. So what this is saying is that you can find local coordinates so that not only is the Hessian diagonalized, but in fact the whole function's given by its Hessian. So i.e. F is given up to this constant by its Hessian in these coordinates. So this is the first basic result about non-degenerate critical points. And I'm going to assume F vanishes at the origin. Just okay. Make the argument slightly easier to present. So the first basic fact is that suppose you have a C infinity function defined in a neighborhood of the origin and G of 0 is 0. Okay. Then G can be written as summation xi hi of x1 to xn in some local coordinates. Certainly any function of this form, summation xi times functions hi of x1 to xn vanishes at the origin. And the converse is also true. And this is a very simple and very beautiful argument. Since G of 0 is 0, by the fundamental theorem of calculus, G of x is the integral from 0 to 1 of d by dt of G of tx integrated against dt. Right? G at 0 is 0. This function takes value 0 at 0 and G of x at 1. Differentiate and integrate from 0 to 1, you'll get the difference. Okay. On the other hand, by the chain rule, this is the integral from 0 to 1, summation over I of partial of G with respect to xi at tx times the derivative of this thing with respect to t in the I direction. So that's xi. So then you just write this summation over I xi integral from 0 to 1 dg dxi tx, dt here, dt. And this is the function hi. Okay? So that's for a function vanishing at the origin. If you use this argument twice, you get a nice expression so for functions that vanish at the origin and whose differential is 0 at the origin. So now suppose both that G of 0 is 0 and the differential of G at 0 is 0. Then you get in local coordinates y1 to yn, G is summation over I and j, I'm being sloppy here about whether my indices are up or down, but yi, yj, hij of y1 to yn. Just apply this argument twice. And of course, hij at the origin, well, make the hij symmetric by simply averaging then hij at the origin is the second partial of g with respect to xi with respect to xj at the origin. Okay. All right. So so now we're going to apply this lemma or this claim. But first we're going to arrange that. So now we're going to make the Hessian of f at the origin diagonal with values down the diagonal, epsilon 1, epsilon n, the epsilon I are plus minus 1. So by a linear change of coordinates, I can turn the Hessian into a diagonal matrix with plus and minus 1s down the diagonal. I don't get any zeros because I'm assuming this is a non-degenerate critical point. So the Hessian only has plus and minus 1 eigenvalues. That diagonalization is done by a linear change of coordinates. I can apply that linear change of coordinates, linear automorphism to the change of coordinates to get a change of coordinates, so that in fact I have local coordinates in which this is the Hessian diagonal. Okay. So in appropriate local coordinates. Inappropriate local coordinates. And I'm going to use those coordinates. I'm going to start modifying them. Well, I know that f in these coordinates is summation over I and j, xi, xj, hij of x1 to xn, and the hij are symmetric. Okay, so I'm going to, one step at a time, make this function begin to look like it's Hessian. So let's start with y1 equals the square root of epsilon 1 h11, I'll talk about that in a second, times x1 plus epsilon 1 h1I over square root of epsilon 1 h11 times xi. So what kind of expression is that? So first of all, I need to be able to take the square root of epsilon 1 h11, but h11 takes value at the origin epsilon 1, and therefore this expression, this function takes value 1 at the origin, and therefore in some neighborhood is positive, and I'll work in a neighborhood where I can take the square root. Okay. Now, if you square y11, you will get epsilon 1 h11 from that, x1 squared, plus 2 epsilon 1 h1I x1 xi plus something that only involves something xi xj summation I and j greater than or equal to 2 times some stuff, which I won't write down, but functions of all the variables. Okay, so if I take epsilon 1 times y1 squared, I will get h11 x1 squared plus 2 h1 sum, this is summed over I, sum over I, h1 I x1 xi plus other stuff that only involves, has in front of it xi xj with I and j greater than or equal to 2. Okay, well, this is exactly the terms in the original expression that have an x1 out front. I have twice h1 hi here, x1 xi, and because the hij are symmetric, that accounts for both the h1i terms and the hi1 terms. And this, of course, is the leading term. So we see that we have managed to write this thing as epsilon 1 y squared plus summation over I and j greater than or equal to 2 xi xj, and some now different functions, but I won't change the names, hij of x1 up to xn. So I've peeled off, by making this change in the first variable, I've peeled off a new coordinate, y1 squared, which has the form I want, and I'm left with these products involving only x, I, x, j for I and j at least 2 times a function of all the variables. I just continue like this until I get epsilon 1 y1 squared up to, and the last one is epsilon n y n squared. And in those coordinates, f is equal, f is of the form that I want. Okay. So that's the first basic theorem of Morse theory. In a neighborhood of a non-degenerate critical point, there's a canonical form for the non-degenerate critical point. There's only one model up to translation by the value of the function at the critical point. Yeah. So any coordinates like these, the yi are called standard coordinates for f near this non-degenerate critical point, P. And we will use these standard coordinates over and over and over again. We will see how to extend them, how far we can extend them, and so on. They'll be crucial in everything that we do. Okay, so it's time to go back to the definitions now. A function f from a compact smooth manifold to the reals is Morse. It's a Morse function, or is Morse, if all critical points are non-degenerate. By what I've just seen, the local model tells you a non-degenerate critical point is the only critical point in some neighborhood. If you look at the local model, there are no other critical points in that neighborhood, and therefore on a compact manifold, the Morse function has finitely many critical points. Each of these critical points has an index. The index of a critical point P is by definition the index of the Hessian at P of F. So we have a finite number of critical points. Each has an index. Now, as we go along, we're going to need to work with manifolds with boundary. So I want to introduce the notion of a Morse function on a manifold with boundary. So let's let W, let's say compact manifold, compact smooth manifold with boundary. We need a decomposition of the boundary of W into two pieces called boundary minus of W and boundary plus of W. Each of these pieces is a union of components. Connected components. Okay. Then a Morse function with respect to all this structure, W to R, okay, it has the following properties. It's locally constant on the boundary. All critical points are in the interior of W. So when you have a compact smooth manifold with boundary, any function on it is by definition of what smooth means, can be extended in a local coordinate patch to a small neighborhood. So there is a differential defined on the tangent space to the manifold at the boundary, which will still be an n-dimensional vector space. And so when I talk about critical points, I mean the Hessian of that map would be non-degenerate. So the Hessian of the map along the boundary is required to be non-degenerate. Since it's locally constant on the boundary, that means these, I mixed myself up. The differential of the map along the boundary is non-trivial. Since it's locally constant on the boundary, that means in the normal direction to the boundary, either in or out, and we choose to think about outward pointing tangent vectors. So if x is in boundary plus of w, the differential of f on an outward pointing tangent vector is positive. And if x is in boundary minus of w, the differential of f at an outward pointing tangent vector to x is negative. So our picture is, here's the manifold with boundary, and here's an outward pointing tangent vector. If this is part of boundary plus, then the function is increasing. So f is increasing as we go in this direction. Over here we have boundary minus, and f is increasing as we move into the manifold. Okay. All critical points are in the interior of W and are non-degenerate. So this is a Morse function in the sense that all its critical points are non-degenerate. In addition, the function is locally constant on the boundary, and that gives us a division of the boundary into those points where the function is increasing as you approach the boundary, and those points where the function is increasing as you move away from the boundary. The former are W, boundary plus of W, the latter are boundary minus of W. So functions on manifolds with boundary have these restricted properties near the boundary. Just as an example of how these arise, suppose that M is a closed manifold, smooth manifold, and F is an ordinary Morse function, and A and B, say A less than B, are regular values. Okay, so then F inverse of AB, maybe I'll call that W of AB, inside M is a compact manifold with boundary. The boundary of W is F inverse of B, disjoint union F inverse of A. This is boundary plus of W, and this is boundary minus of W. And the picture is simply, here's the manifold M, here's the level set B, here's the level set A, and here's the manifold W, A, B, and the function is increasing in this direction. So this is boundary minus, and the preimage of B is boundary plus. So that's the typical way that even if you're only interested in closed manifolds, you end up studying manifolds with boundary, and notice the function's clearly locally constant on the boundary. All right. Next theorem goes back to Morse. So M is a compact manifold. Without boundary, let's say. Then the set of Morse functions is an open dense set of inside C infinity in C infinity, in this space of C infinity functions. So there are Morse functions, and you can approximate by an arbitrarily small deformation any C infinity function by a Morse function. Well, let me reformulate what it means to be a Morse function. So f is a Morse function if and only if df, is differential of f, mapping m into the cotangent bundle of m, is transverse to zero, to the zero section. Okay, the critical points will be the pre-image of the zero section, and this condition on the Hessian that it be non-degenerate is just the condition that d of df at p, or projection under the second factor, mapping the tangent space of m to the cotangent space of m, is an isomorphism. The Hessian's non-degenerate if and only if that map is an isomorphism, which is exactly the condition that the map, so here's the cotangent bundle, here's the map of the manifold df. The condition that df be transverse to the zero section is that the projection of the differential onto the vertical space be an isomorphism. Right? Well, to be transverse to the zero section is an open condition. That's completely clear. And the fact that there's a open, that this is also gives a dense, there's a dense set of functions to satisfy this condition, is a simple transversality argument. So this implies obviously open and transversality is a G delta condition by, say, Thomas transversality argument. Anyway, whatever your favorite form of transversality is. Okay. So the set of Morse functions is an open dense set. I won't go through the details, but the same argument works for manifolds, compact manifolds with boundary. There's really no difference because we've assumed there are no critical points on the boundary, so the map of the compact manifold with boundary into its cotangent bundle, under that map, the boundary is just joined from the zero set, so you just do transversality in the interior by the usual argument. Okay, so we have lots of Morse functions. We can approximate any smooth function by a Morse function. Okay. Let me give you a couple of approximation results that will be useful later. Let me just see what I want to do here. Yeah, so one addendum or generalization of this is, suppose you have a manifold, doesn't have to be compact, a C infinity manifold, and a function R, C infinity function R. And suppose the critical set is compact. So of course it's always closed, so if W were compact, this would be automatic, but in general, suppose it's compact. Then there exists a more, well, choose any neighborhood, C in some neighborhood, an open neighborhood in W, small as you want. Then there exists a Morse function G W into R, with G restricted to the complement of U equal F restricted to the complement of U. So you only have to change the function to make it a Morse function in an arbitrarily small neighborhood of the critical set. In fact, you can do this without the compactness of the critical set, but I won't talk about that. So you do this perturbation locally around the critical set. Another addendum is that if, under the same hypothesis, if the Hessian at every C in C has at least K negative eigenvalues, which we can take to be, so the number of negative eigenvalues in general we take to be the index, whether or not there's zero eigenvalues. So if the Hessian at every point of this critical set has at least K negative eigenvalues, so its index is at least K, then the same is true of the Morse function, the approximating Morse function. And the point there is that inside quadratic forms, to have at least K negative eigenvalues is an open condition. If you have some zero eigenvalues and you deform the quadratic form slightly, well, the ones that were negative will stay negative, the ones that were positive will stay positive, the ones that were zero will get split somehow between positive and negative. How many of each type will depend on the deformation, but nevertheless, you'll still retain all the K negative eigenvalues that you started with, and you might get more. So in fact, the index of the Morse function approximations lie between the index plus the nullity, the number of zero eigenvalues, and the index. So that's the range in which you can get critical points. Okay, and let's see. And one last corollary, approximation corollary, the set of Morse functions with only one critical point at each critical value is also an open dense set. Since the set of Morse functions, this is on a compact manifold, since the set of Morse functions is an open set, certainly the condition that distinct critical points have different values is an open condition. So putting on that extra condition still gives you an open set. And again, it follows easily from transversality that it remains dense. Okay. We will be working with Morse functions. Well, we'll actually be working with what are called self-indexing Morse functions. These are Morse functions where the critical value at a critical point is equal to its index. So they won't have this property, but in order to get there, we need to be able to move the critical points around. And for example, start with a Morse function where the critical points have distinct critical values. Yeah, how am I doing on the time? Okay. So let me give you a finite dimensional analog of this infinite dimensional theorem that Morse functions are open dense. We don't need this, but it's a very nice finite dimensional analog, which helps give you a sense of Morse functions. So I thought I would show it to you. So we're going to work now with a manifold smoothly embedded in some large Euclidean space in this compact, smoothly embedded. Okay. Then for any unit vector in the ambient space, we have a function fu on the manifold, namely fu of m is simply the inner product of M and U. This is the Euclidean inner product in the ambient space. So you have some Euclidean space, you have a direction, and then a manifold, and you're just restricting the level sets of this function are simply the coordinate, the intersection of the coordinate hyperplanes perpendicular to the direction with the manifold. And if you choose a generic direction, so the theorem is for U, well, there's an open dense set of U that give you Morse functions. So there exists an open dense set mu in the sphere such that F mu is Morse. Okay? So the analog of the density of the Morse functions. These particular Morse functions are dense. Let me just sketch the proof. So let's define a vector bundle over M whose fiber at X, sorry, it's not a vector bundle, it's a locally trivial fiber bundle, whose fiber at X is the Grassmannians of codimension 1 linear spaces in the normal bundle, the perpendicular to the tangent bundle at X in Rn. Okay, so if this is the manifold, here's a point, we have the tangent bundle, we have the orthogonal complement in Euclidean space, and I want in that orthogonal complement a codimension 1 subspace. And so the fiber here will be the projective space on a Euclidean space, a vector space of the complementary dimension. So it'll be a real projective space of total dimension capital N minus little n minus 1. Okay. Now there's a map from the total space of this bundle to the Grassmannian of codimension 1 spaces in the ambient space. Given a point and a linear subspace, you simply take the direct sum of the tangent space of the manifold plus that codimension 1 linear subspace, and that's a codimension 1 linear subspace in the ambient space. So let's call that map phi. And then it's easy to check that the critical points of Fu are simply the projection to M of phi inverse of the perpendicular space to U. Call that V perp U. So this is the space perpendicular to U. So those are the critical points. And the map is Morse. So Fu is Morse if and only if Vu is a regular value for phi. Okay. So there you have it. You need to find a regular value in this Grassmannian, which the Grassmannian is just the sphere by perpendicularity. So you need a Grassmannian or a perpendicular vector that's a regular value for this map, and the standard result of standard version of Sard's theory tells you that the non-regular points, the critical points of the map, are nowhere dense, and therefore the regular points are dense, and because things are compact here, they're an open dense set. All right, so that's this finite version of Morse theory. It's a very simple regularity theorem. And the last general comments I want to make about Morse functions are to introduce a generalization, functions that are not Morse, but for which you can do much of Morse theory. And these are called Bott Morse functions. So I emphasize they're not Morse functions, they're weaker. But here's their definition. So we'll work with a closed manifold, a C infinity function. And the function is Bott Morse if it satisfies the following properties. First of all, the critical set of F is a smooth manifold inside M, smooth submanifold inside M. Now, this has to be taken in the general context. The smooth submanifold can have different components, and those components are allowed to be of different dimension. Okay, but that's what I mean by a smooth submanifold. Secondly, the null space of the Hessian at a critical point P of F is the tangent space at P to this smooth submanifold, which again can vary dimensions as I vary P. Okay, so P here is a critical point. We have its Hessian. Hessian has a null space. The null space will certainly include always the tangent space. In fact, this is a risky tangent space to the set of critical points. This is a manifold, so the risky tangent space is equal to the naive tangent space. And the condition 2 says the Hessian is exactly of that dimension. It's exactly the tangent space to the critical points, no more. And that's it. That's what a Bott Morse function is. Notice that if you had a Bott Morse function and the smooth submanifold of critical points was a discrete set of points, a finite set of points, then the tangent space to that finite set of points is the zero vector space, and the null space of the Hessian would be 0 at every point. So Bott Morse functions, where the critical set is isolated, consists of isolated points, is an ordinary Morse function. Of course, if the critical set has a component that's a smooth manifold of positive dimension, then that's not a Morse function, but nevertheless it can be Bott Morse. Now these functions appear in geometric context when there's a group of symmetries on, you have a manifold with some symmetries, and the most natural functions to study are then maybe the functions invariant into those symmetries. All you can hope for is that you'll get Bott Morse functions rather than Morse functions, because the critical set will be invariant into the group action. Okay, there is, yeah, okay, I don't think I'll say anything more. We will see Bott Morse functions when we start proving Bott periodicity. The natural way to work there is there's a symmetry group, and the natural functions are Bott Morse functions, and we can actually use those. That's the way typical proof of Bott periodicity. All right, so that's the basics of Morse theory. I now want to start studying some simple cobordisms with respect to Morse theory, the simplest cobordisms with respect to Morse theory, and understand what they look like. So these are going to be elementary Morse boardisms. Okay. So the most elementary of all Morse boardisms, these are now going to be compact manifolds with boundary and the Morse functions on them. So suppose we have a Morse function on a compact manifold with boundary, Morse, with no critical points. No critical points at all. Well, that forces W to be a compact manifold with boundary. And remember, we're requiring F be locally constant on the boundary and have no, well, it has no critical points anywhere, so it has no critical points on the boundary. Might as well take F connected for this. Okay, so notice this implies boundary of F is not equal to the empty set. And we have the division which comes from the Morse function, boundary W is boundary minus W, disjoint union boundary plus W. Okay. Where the function is increasing as we can move away from the boundary, and where the function is decreasing as we move toward the boundary. Sorry, increasing. Boundary minus is where the function increases as we move away from the boundary. Boundary plus is where the function is increasing as we move toward the boundary. Okay. Well, the study of all these elementary boardisms, and in fact, all Morse theory, uses in a crucial way what are called gradient-like vector fields. So let me introduce those. So a gradient-like vector field is a vector field chi on W or M with two properties. One, if P is regular, dF at P evaluated on chi P is positive. So here chi P is a tangent vector, dF at P is a cotangent vector. You just have the usual pairing between them. That's positive. Of course, another way to write this is dFP on chi P is simply the derivative of F in the chi direction at the point P. Okay. So at any regular point, this evaluation, F is increasing in either of these say that F is increasing in the chi direction at the point P, and at a critical point P, there exists standard local coordinates such that F is equal to F of P plus summation epsilon I plus minus 1 xi squared, and chi is summation 2 epsilon I partial x xi partial with respect to xi. Okay, so in other words, in these local coordinates, chi is the gradient of F. Okay. So we have two conditions, a local condition around every critical point with respect to some standard coordinates, and an increasing or positivity statement everywhere it's possible, that is everywhere the function does, at all regular values of the function. Okay, and the first little lemma is that there exist gradient-like vector fields. For any Morse function. That is to say, given a Morse function, there exists a gradient-like vector field for it. Okay. Well, proof. There are many proofs, but let's do this one. Choose a Riemannian metric. That near each critical point is the Euclidean metric in a standard coordinate system. Well, in the standard, a standard coordinate system. Okay. So to form a Riemannian metric, we cover the manifold by open charts, take a standard metric in each chart, and then patch together with a partition of unity. Make sure that the critical points are only in one patch, and you take the standard Euclidean metric in that patch with respect to standard coordinates, and then when you do the partition of unity averaging argument, you won't change the coordinates near that point. So you'll have a Riemannian metric with this property, and then you just take the gradient with respect to this metric, G of F. So since the metric is standard near each critical point, the gradient of this function is given that way, near the critical point, and the value of df on the gradient is simply the norm of df at p squared in that metric, which is positive, since df is non-zero. There are many other ways to produce gradient-like vector fields, but they all involve patching together. Okay, so now let's go back to our elementary boardism. So F mapping W to R, W is compact manifold with boundary. This has no critical points. Okay. We choose chi, a gradient-like vector field. Okay. The first thing to notice is that chi F at P is positive for all P in W, since F has no critical points. But W is compact, that means chi F is bounded away from zero. On all of W. So in fact, F is increasing in the chi direction by at least a fixed positive amount, by an amount bounded away from zero, independent of where we are. Okay. Now this manifold is compact, so F takes a maximum value, F takes a minimum value. So here's the maximum value. Here's the minimum value. And here's any point in the manifold. Since the manifold is compact, we can integrate the vector field to get a flow through this point, which will continue until we hit the boundary. And if we flow backwards, it will continue backwards until we hit the boundary. Or, well, because so one possibility is that you have recurrence. You know, you could have a vector field with a closed orbit, for example. You just go round and round and round. But our function is increasing at a fixed rate. Therefore, no flow line can continue for an amount longer than that fixed rate times the difference between the value at the point you start with and the maximum value of F. So you start here, F has some value. As you move along the flow line, as a function of t, F is increasing at least a fixed rate. You eventually have to hit the maximum value. And likewise when you move backwards. So that says no flow line can go on forever, and therefore every flow line has to go from boundary to boundary. Clearly every flow line goes from boundary minus of W to boundary plus of W, since these are inward flowing and here they're outward flowing. So the trajectories of this gradient flow are flow lines that start on boundary minus and end at boundary plus. And F is increasing along the flow line. So now we're going to define a function from the manifold to, to boundary minus W cross R. So to a point W, we associate what I'll call Y of W and F of W. So if this is W, this is Y of W. So Y of W is the initial point in boundary minus W of the flow line through W. Well, that by existence, uniqueness, and a smooth variation with parameters, that's a smooth map from capital W to boundary minus, and this is a smooth map. It's easily seen that this map is an injection. And the maximum value is F of boundary plus W, because the value at any point increases as you move up to the boundary, and the minimum value is F of boundary minus W. And so in fact, we have an embedding of W into boundary minus W cross AB. Did I give names to the maximum and the minimum? No. Min and max, whatever they are. And it's easy to see that's the isomorphism. Okay. So did I even state a theorem? What I've just proved is that theorem, if F mapping W into R is a Morse function with no critical points, then W is diffeomorphic to boundary minus W cross AB by a diffeomorphism such that F is projection to the second factor. Okay. All right. So those are the simplest kind of boardisms. Next most simple are those with a single critical point. So let me just and I think I'll start the discussion of a single critical point on Wednesday. So on Wednesday, we begin with FW to AB, let's say, with exactly one critical point. We'll study these as well and understand their topology. And then from there, we'll move on to self-indexing Morse functions and what's called the Morse complex, which computes the homology of the manifold of W rel W minus. I'll do all of that next time. Any questions before we disband? So today I used the landscape version of the iPad rather than the portrait version. And I switched between having two columns when I was giving simple definitions and just using the whole space when I was stating propositions or using them to prove theorems. Do you find this works better as well as or not as well as the portrait mode? Any reaction to that?
What's more comfortable for you? It's easy to read.
It's okay to read. Yeah, I actually like having a wider space to work with.
Yeah.
So people didn't have trouble with this. Any content questions? Any mathematical questions?
Well, I
Well,
think
if no one else does, in your notes for today, there is one sentence that was like falling into a black hole, which was, for all Morse functions sufficiently close to f, we have a one-to-one correspondence of critical points preserving the indices. So there are a lot of groups that could be colliding there. I mean, the fundamental group of the manifold, the fundamental group of the space of all Morse functions, the symmetric group of the critical points, monodromy-like thing around a thing that's not quite a Morse function.
Yeah.
Are we going to get juice out of that?
When we start studying Cerf's theory on pseudoisotopies, we will touch on some of those issues. We'll have to follow the critical points around. All that we're going to do to prove the H-cobordism theorem, which is our first subject, is, so first of all, that was a local theorem, right?
Mm-hmm.
You have a finite set of, you have a Morse function has a finite set of critical points. You're going to move it a very small amount. And what's going to happen is those critical points are going to move a little bit, so small that they don't collide with each other or wrap around each other or get confused in any way. So you have a bijection between the critical points of all the nearby functions because they haven't moved very far. And under that bijection, the indices are preserved. That was the statement I was making there. We will, as you'll see, I guess in the next lecture, so maybe on Wednesday, we will have an example of what's called a birth, where you have no critical points at all. You go through a degenerate critical point, and suddenly two critical points of different index, R and R plus 1, are created, and then those can move apart. And we'll take one of them and move it over near another critical point and collide it with the other critical point, collapsing them. So we will do those kind of motions, but we're not studying at this point monodromy or action of the symmetric group or anything like that. I mean, that we'll get closer to that kind of discussion when we get to pseudoisotopy. But here our motions are very simple and one-dimensional, really. Other questions?
and maybe a kind of dumb question. For the standard form near a point, is it like kind of unique up to a linear transform?
Not quite, interestingly enough. So you're certainly right. I had to choose the linear transform. But then even if you fixed that, so you fixed the Hessian, I mean, you fix the coordinates up to second order. The order of the coordinates matter. I did an argument which ordered the coordinates, and I first worked on the first one, and that screwed up all the others, and then I worked on the second one, and that screwed up the remaining ones, and so on. If you do it in a different order, you will get a different standard coordinate system. It's very, I mean, just work out the formulas when there's two coordinates, and you'll see that you get different answers. So the coordinates are not unique. I don't know, is the set of all of them connected? I don't know. I have never thought about what the set of all standard local coordinates looks like. We will use, when we talk about these one parameter families of bursts, we will use the fact that through the whole system, there's one parameter family, there's one set of standard coordinates. But I don't know what, so that's an interesting question. Just think about it. What all the space of all standard coordinates, you know, it's a local question around a singularity in Euclidean space. What does that look like? I don't know. I mean, it certainly has an action. Well, let me not say anything more. Any other questions? What about the pace? So Dave said it was easy to read my writing. I'm glad to hear that. What about the pace of the lecture? How much I write down? Because I'm getting no direct feedback from you, I have no idea whether I've lost everyone, whether it's completely obvious to everyone, whether or not the pace I'm going at is one that's suitable for the audience. So I would welcome feedback. If you don't want to give it orally over the air, you can just send me an email. But I would welcome any feedback about the pace, the level of the exposition, and so on. I will just say it's about this pace I will have to go to cover everything I'm hoping to cover, or in fact, only get 80% of the way toward covering everything I'm hoping to cover. All right. Well, if nobody else has anything, I will see you Wednesday, same time.
Thank you.
Yeah, so long.
You